Hi, good afternoon. And thank you, Lorella, for such a kind introduction. It's been a while since we met in person, and I miss you dearly as a friend and an exceptional colleague. I thank the committee and Carlos for bringing me to this conference. It's been very exciting. There's a lot of great exchange of ideas, and I'm just honored to be a part of it. We are just starting our morning here, so we'll be sipping my coffee if that's okay to freshen up. But it's great to see you or see you virtually. So our lab specializes in the use of non-invasive brain stimulation, primarily RTMS, TDCS, for patients with stroke. Wanted to check that everybody could hear me okay?
Yes, we can.
Okay, thank you. So our area is especially in patients with severe stroke. Stroke, as we know, affects several different modalities in the body, but we're primarily focused on motor function and motor function of the upper extremity, because that takes the major brunt after a typical middle cerebral artery infarct stroke. So making sure I can. All right, so the objectives that I would like to meet today and then open up for a lot of useful discussion is to weigh whether there is enough evidence to suggest that therapeutic neuromodulation techniques such as RTMS, TDCS, theta burst are effective at retraining motor function after stroke. That is really a big question, and you'll see why that is the case because of divided evidence from many clinical trials. So the techniques we use in the lab are absolutely not unfamiliar to you. They include techniques like single pulse TMS, paired pulse TMS, as shown in this example, use of bipulse TMS for measurement of what we call inner hemispheric inhibition, a model that I've really tried to explore with Lorella through her work as well in the area of other modalities besides motor function. So none of these techniques are unfamiliar to you, just walking you through this. What we also use in the lab is repetitive TMS, again, something that Lorella and I have used quite a bit since I got to know her during my postdoctoral fellowship, where she was leading studies in this area for visual attention and visual attention cognition. So with use of repetitive TMS, there are several different protocols, as you all know. The protocols that we are interested in include high-frequency repetitive TMS for facilitation of motor cortical areas. What those areas would be, we will discuss in a second. Other techniques we use in the lab include TDCS. Our dear colleague Daria was talking about that in the context of her work. So we use that as well. And then several imaging techniques, which involve MRI, just the T1 weighted MRIs, because we're working with stroke. So understanding the lesion location volume is critical. Diffusion tensor imaging, because the primary insult in stroke of a typical middle cerebral artery stroke lies with the internal capsule and the damage to corticospinal pathways. So that's where we're using diffusion tensor imaging to characterize the extent of injury. And then functional MRI, again, something that we had discussed in the last session as well. The primary fundamental premise that drives our research program is that the intact neural resources can serve as important targets for recovery. And you'll see this that in the area of stroke, there has been somewhat of a cacophony. We've really tried to focus on areas that are supposed to be working, that are located in the lesioned hemisphere, such as the primary motor cortex, as the most favored target for brain stimulation. But we will realize soon that the evidence about its effectiveness is quite mixed and is very divided. So the goal of our research program in our lab is to not bank on what used to be and what should be, but it is on what is available to the patient. So the burden of stroke in the United States and even globally is just enormous. It is the leading cause of long-term disability among adults in the United States. There are now estimated to be 8 million stroke survivors in the United States alone. And the cost of the long-term disability associated with stroke is tremendous. Um, in the context of the United States and the clinical demographics, we realize that the major deficit following a stroke is the loss of upper extremity or upper limb motor function. And so patients continue to experience residual deficits. Rehab is given for the first month or first few weeks. And after that, the patient is left to their own resources because of insurance and payer issues. And because of that, the chronic disability from stroke is actually quite high in our country. And therefore, it becomes a major economic burden as well. Patients are graduated or discharged from hospital facilities and skilled nursing facilities without really being given the tools to properly incorporate the use of their upper extremity in their daily function. So let's talk about what are the current rehab approaches. I am a physical therapist by trade, and so this is extremely dear to me. Is bringing back the function to an individual patient. So the rehab approaches that I have used in my practice, and we continue to in our practice along with other colleagues, is one and only one, which is let's incentivize use of the weak upper extremity, but really de-incentivize the use of the good hand. Because the good hand is supposed to be a competitor, it affects the recovery of the weaker hand. Patients tend to rely on the good hand just too much, and then any possibility of recovery of the weaker hand is further reduced. And so, if you have patients performing rehab therapies, we ask them to use constraint of the good hand. For instance, putting their good hand in a mitt while performing activities with the weaker hand, so that more and more we can exercise and we can capitalize on the plastic processes that we believe to be available to these patients. Now, what happens is that the effectiveness of these therapies, such as constraint induced movement therapy, which incentivize use of the weak hand, but really de incentivize use of the good hand and constrain the use of the good hand. Those have been highly effective for patients who are very mild in their dysfunction following stroke or mild to moderate, because you need enough function in the upper extremity, in the weaker extremity, to actually be able to put it to good use during functional training. But if you don't have that amount of function, if you don't have the amount of residual function that is necessary, you can't use your hand in performing the activities during rehab. Therefore, what we find, and this is reported across evidence from global groups, that use of techniques which de-incentivize use of the good hand and which believe the good hand and the good hemisphere to be a competitor is just infeasible for severe patients. They just don't have the function in the weak hand. So either they need a lot of assistance from others, or they need a lot of assistance from the good hand to be able to perform rehab. So all of this current rehab is based on a model of stroke recovery, which was launched from colleagues at NIH here in the United States, Dr. Leo Cohen and his group, and is a very popular model that we have followed and others have followed. What this model basically says is that if you look at healthy volunteers and you measure bihemispheric or interhemispheric inhibition, you realize that during movement of a unilateral upper extremity, that the other hemisphere has always imposed a lot of interhemispheric inhibition. But whenever you need to perform unilateral movement, that inhibition from the opposite hemisphere alleviates, and instead you're able to see a facilitation and thereby perform movement. But in the context of patients with stroke, they persistently experience interhemispheric inhibition from the opposite motor cortex. So, saying that the weak motor cortex is unable to perform the intended movement because the intact motor cortex serves as competition or imposes tremendous competition to that movement. So the patients have a harder time performing the movements. So the stroke itself has damaged the corticospinal resources necessary to perform the unilateral movement. But on top of that, the good cortex or the intact cortex is so competitive so that it further compromises the ability of the patient to exercise any movement from the affected or the weak extremity. And so this is where this theory is known as the interhemispheric inhibition theory of stroke recovery, saying the weak hemisphere is really weak, but the good hemisphere is really competitive, and it's weakening the weak hemisphere further. Therefore, there's only two types of solution, and the solutions would be to really, really exercise use of the weak extremity, but really de-incentivize the use of the competitive intact extremity. So an example from Miraz and Cohen's work shows that as patients are more severe, you see deeper and deeper interhemispheric inhibition from the intact motor cortex. And this created and launched the most pervasive theory of brain stimulation in the area of stroke upper extremity motor recovery. The idea that the intact hemisphere is competitive, is too inhibitory, and the more inhibitory it is, the weaker the function of the individual. Therefore, to improve the function of the individual, it is best to shut off the intact hemisphere. So this is an example that lesion hemisphere is weak. Interhemispheric inhibition from the opposite or the good hemisphere is too high. And therefore, moving the good hand would help us change this balance or increase the interhemispheric inhibition. So instead, we should excite the lesioned hemisphere, increase use of the weak hand, and constrain use of the good hand. But there have been several challenges to this current model. And these challenges include that we have seen and others have seen for quite a long time that in severe patients, it is the intact motor cortices in the intact hemisphere that tend to reorganize in association with recovery. We've seen this with fMRI studies. We've seen these with TMS studies. So the maps in the intact hemisphere start to expand in association with motor functional improvements. We also find that intact hemisphere offers uncrossed pathways to the paretic extremity. And here's an example from a patient where the crossed pathways produce very small levels of motor evoked potentials, but the uncrossed pathways actually produce much larger potentials in the same paretic muscle. Meaning that in these severe patients, though TMS is unable to elicit potentials from the crossed pathways, TMS is able to elicit potentials from the uncrossed pathways to the same weak muscle, suggesting that the intact hemisphere may offer some adaptive, alternate uncrossed pathways as useful resources for movement recovery. And a lot of work done by colleagues who presented yesterday, Bestman and colleagues, that say that intact hemisphere actually may have a causal influence in movement. So if you do virtual inactivation or knockout experiments in patients who are more severely affected, you'll be able to see that knocking out the intact hemisphere, but not the lesioned hemisphere, creates disruption in movement, suggesting that in severe patients, the intact hemisphere may have causal, even though partial, even though not fully restorative, but may have causal influence in the movement of the paretic extremity. We have also found this in our own experiments. For instance, when we have performed studies, such as one done by my graduate student and a colleague in our lab, when we have performed studies where we have asked patients to use the good hand while they're moving the weak hand, we have found a flip of the interhemispheric inhibition model. And this will become clear in just a second. So in this case, we're having patients either perform unilateral electrical stim-based movement of the weak hand, or the other newer intervention developed by my colleague here, Jamie Knudsen, which is contralaterally controlled functional electrical stim, where forces from the good hand are used to initiate electrical stim of the weak hand. So almost consider this as a bilateral task, okay? Going against the usual theory that you should not use bilateral treatments in patients with stroke. So what we have done in this study is use TMS to measure crossed pathway or the crossed MEPs. We have also used TMS to measure the uncrossed pathway potential from stimulation of the intact hemisphere. And then we have used interhemispheric inhibition and its measurement with bihemispheric TMS. And what we have found is that with the bilateral treatment, known as CCFES, we see a greater reduction in interhemispheric inhibition from the intact hemisphere. So the bilateral use of the extremities is causing a much greater reduction in the competition that is generally levied by the intact hemisphere. We also found that the uncrossed pathways from the intact hemisphere became slightly more excitable and significantly more excitable compared to just unilateral stimulation of the weak extremity when we get delivered bilateral stim. So overall, when we are using bilateral stimulation in patients with stroke, we're finding that that interhemispheric inhibition that was always believed to be higher in such patients is actually more reduced with the use of bilateral than unilateral treatment. And that when we're giving bilateral treatment, the excitability of the uncrossed intact pathways to the paretic extremity is more significantly increased compared to when we just give unilateral movement of the weak hand. What we also find is that there is a severity specific association of these mechanisms. That means the more severe the patients were, the more reduction they were able to see in interhemispheric inhibition, and the more excitation they were able to see of the uncrossed pathways to the weak extremity following bilateral treatment. That means for patients who are so severely affected, who really don't have much use of their weak hand, the use of the good hand together in concert with the weak hand helped normalize or helped to some degree rebalance the two hemispheres and recruit the potential of the intact pathways because much crossed pathways do not remain in such patients. So overall, based on several lines of evidence, it is now realized that the intact hemisphere reorganizes with recovery in patients with stroke, is not always competitive and inhibitory, has uncrossed pathways that can serve as alternate resources when the crossed pathways have suffered from the insult, that the intact hemisphere can actually reduce interhemispheric inhibition and increase the contributions from the uncrossed pathways to serve as helpful resources for paretic extremity movement, especially with bilateral therapies. And it may have, therefore, the causal influence that Sven Bestman and others had highlighted in patients who are more severe. So the role of the intact hemisphere cannot be just maladaptive, unilaterally maladaptive, that it is more nuanced and maybe more helpful for patients who are more severe. And this has launched the second line of treatments that we give in our lab. In our lab, we focus not just on use of the paretic extremity, but use of the non-paretic extremity in concert with the paretic extremity. And therefore, the brain stimulation approaches we have developed are also not univariate, simply trying to increase the excitability of the weak lesioned motor cortex, but are actually trying to do the opposite, which is excite the intact motor cortex in patients specifically with severe stroke. So how did we test that? I'm going to try to jump ahead. How do we find that the current model does not work? The current model of brain stimulation, like I said, is either just exciting the lesioned hemisphere or shutting off the intact hemisphere. These are the only two approaches that have been conventionally used. And earlier clinical trials were very, very promising. They saw a great effect with either increasing the excitability of the lesion motor cortex or shutting down the excitability of the intact motor cortex. But what happened is that even though there was a lot of translational evidence to back the conventional method of stimulation of exciting the lesion motor cortex and shutting off the intact motor cortex, it failed to translate to many phase 2 and phase 3 trials. There is now a longer list of phase 3 trials that have adopted this method in patients with mild to severe spectrum of stroke and have found this to specifically fail at the level of large clinical trials. And we have published a lot as to why these trials have been consistently negative in the area of brain stimulation for stroke. And ultimately, these trials have helped to summarize that the functional gains in these trials have been most limited in the severe patients. These severe patients who have been given excitation for the lesion motor cortex, which may not anymore be a useful resource for them, or have involved shutting down the intact motor cortex, which may be the only partial, though available source for their functional restoration. And therefore, this has forced us to question as a field the utility of the conventional method of brain stimulation in patients with severe motor stroke. And so we published upon the evidence that when you look at phase 1, 2, and 3 trials, in this case of invasive direct motor cortical stimulation of the lesion motor cortex, you find that the phase 3 trials have failed. But when you look at closely the number of patients in those trials that were MEP negative was huge. Only 15% of those phase 3 trial participants had an MEP, but majority, which is almost 85% of patients, did not have MEPs or did not have the potentials from the crossed pathways available. These numbers were much higher. That means there were greater number of participants in the phase 1 and the 2 trials that had these crossed pathways, that had these crossed MEPs. So just by looking at the comparison of these patients and then identifying that if you only consider the 15% of patients in those phase 3 trials that had crossed MEPs and were MEP positive, suddenly the results of this conventional brain stimulation were significant and positive, indicating that the presence of these crossed pathways is critical to the success of conventional brain stimulation that seeks to excite the lesion motor cortex and shut off the intact motor cortex. If these crossed MEPs don't exist, it becomes really difficult for these patients to show greater recovery. And so this is our dissection and that of others using imaging techniques that show that MEP positive status is very important to consider when we're talking about success of conventional brainstem. But what do we do when we don't have those MEPs? What do we do in those severe patients where we don't have these MEPs? So that's where we've created a new technique which does the opposite of the conventional technique. So while the conventional technique, even in severe stroke and large strokes, is forcing us to excite the lesion motor cortex and shut off the intact motor cortex, we're anticipating that the opposite may be beneficial, or at least facilitating the intact hemisphere may be more beneficial for a set of patients, which is patients with severe motor impairments only. So we've conducted these studies where patients have received on a mild to severe spectrum either excitation of the lesion motor cortex or excitation of the non-lesion motor cortex, particularly the contralesional dorsal premotor cortex. And we have measured improvements on motor control assessments of the upper extremity or the paretic extremity. In addition, we have tested crossed pathway excitability from the lesion motor cortex, and we have assessed interhemispheric inhibition. And what we have found is a severity specific effect. So let's go through this, just the less severe patients at this point. And I can talk about what less severe means. But in patients who are mild to moderate in their impairment following stroke, we find that they're finding greater improvements with the conventional method of stimulation that excites the lesion motor cortex. But the more severe patients who are more severe in their motor impairment levels, do not have MEPs in their paretic muscles from crossed pathway excitation, those patients are showing greater effects and greater improvements in motor control with the use of intact hemisphere facilitation. Again, the new technique that we've introduced in our lab and now has been used in other labs. What we find in terms of mechanisms, that in the less severe patients, we see greater gain in excitability of the crossed pathways when we excite their lesioned motor cortex with the conventional stimulation. It is to be expected. They have MEPs, they have residual pathways available. So when you excite those residual motor pathways with the use of conventional brain stimulation, that you see a greater increase in excitability of those pathways in association with their motor control improvements. In the more severe patients, you can see those pathways didn't really exist. Those crossed pathways are at least difficult to read with the levels of TMS we're allowed to use. And therefore, in those severe patients, we really didn't see much change in crossed pathway excitability. But here's what we did see in those severe patients. In those severe patients, if we consider the inner hemispheric inhibition, we found that these severe patients showed a greater reduction in the inner hemispheric inhibition from the intact motor cortex when we facilitated their intact motor cortex, meaning that use of the intact motor cortex and targeting the intact motor cortex and improving its excitability helped create this rebalancing of activity in both hemispheres. And that rebalancing was associated with the motor control improvements were shown by the severe patients. So overall, the less severe patients improve with conventional excitation of the lesion motor cortex based on improvement in excitability of the crossed pathways from that lesion motor cortex. But the more severe patients improve from facilitation of the intact motor cortex in association with a greater rebalancing of inner hemispheric inhibition between the two hemispheres. So it's almost as if in the more severe patients, by exciting the intact motor cortex, we're able to recruit the potential from both the intact and its collaborative lesion motor cortex together. It's like two hemispheres for task of one paretic, very paretic upper extremity. So from this, we've been able to create a model of attempting to at least stratify patients. So with machine learning approaches, we were able to identify that if we're able to look at motor impairment scores in patients, that is the strongest predictor of whether they respond to the conventional or the standard stimulation or respond to this newer form of stimulation that seeks to excite the intact hemisphere. Patients who are more severe, very, very severe, are directly seeming to be responders for the contralesional or the intact hemisphere facilitation. The patients who are more mild to moderate, if they have good DTI values or FA values, they are good candidates for the standard approach of conventional brain stimulation that seeks to excite the lesion motor cortex. But if the DTI reveals that the integrity of pathways is not super, that those patients then tend to be responders to the intact hemisphere facilitation. So from this work completed by two postdocs in the lab, we're able to at least attempt to help stratify patients for tailored brain stimulation approaches based on a combination of their motor impairment score and DTI-based pathway integrity. Also to mention, patients on the left side who were responders to the conventional brain stimulation approach were all MEP positive, whereas patients who responded to the intact hemisphere facilitation as a new approach were all MEP negative. So motor impairment, DTI, and TMS may together help us stratify the best candidates for different approaches. And with this, we've also been able to suggest a revision of the previously acclaimed classical model of inner hemispheric inhibition shown to the left, where patients who were more severe were found to have high inner hemispheric inhibition. What we ended up doing is performing a larger study with patients even more severe on the spectrum. And when we went to the end of severity spectrum in terms of the upper extremity Fugl-Meyer score, we saw that while patients who are mild to moderate show a similar profile of inner hemispheric inhibition as seen in previous study. Extending that severity spectrum shows the opposite, that the very, very severe patients actually have less inner hemispheric inhibition from the intact hemisphere. If intact hemisphere and the intact motor cortices are the primary resources that are available to them, that resource doesn't really need to be too inhibitory or too competitive, because otherwise they wouldn't be able to achieve even partial levels of functional recovery that is possible. So overall, we have tried to answer the question of whether therapeutic neuromodulation or brain stimulation is effective at retraining motor function. And the answer that I humbly sit on is it depends on which patient receives what type of treatment. So with that, I would like to thank all of my colleagues and the grant funding resources in our lab that have made all of this work happen. And I would like to thank the organizers and Lorella for inviting me to be a part of this meeting. Thank you so much.